this equation is going to be uniform. So if you move forward for this one, it's going to be mi, and you want to base the x and to minimize. Okay, the first measurement is it's minus x. This is square. This is a sigma plus sigma y is minus 3. So this is square now. So sigma y is 0.1, and this is sigma 3. So you can get the x by minimize these equations. So actually it's quite straightforward. This one can be formulated as, because this is one-dimensional cases. This will be equivalent to 4.8 minus x over 0.1 squared plus y minus 3x. Minimize this equation and get your solution. It's quite clear, right? You ask a good question. So if I start from here, it's quite easy to understand. Yeah. So for example, for this equation, put the numbers into, you solve these equations, and you get the unknown value. So this is a one-dimensional cases. If you start with 3 dimensions, this is going to be a matrix. Good question. This is a good question. This is a one-dimensional problem, right? It's quite solved. Okay, so let's continue with the following parts. So for this example, okay, so finally this can be transferred to a least square process, right? So if you put this into this least square equations, so this is z minus x, and this is square norm, and this is the sigma, okay, for this one, okay. So this is sigma, and this is also the sigma for second measurements, z1 and z2. So by solving these equations, okay, so let's do this again. So finally, this equations can be, I mean, the log operation of this probability can be transferred into this least square process. So this equation can be transferred into minimize x. Try to find the base x by minimize the z minus x. So the first z1 is 4.9 minus x. This is square norm, okay? So the sigma 1 is the uncertainties or the covariance of the first measurements, and the second one is 1.3 minus x sigma 2 square. Okay, so in this case, so for the sigma 1 is equivalent to 0.1, and for sigma 2 is 0.3. This is 0.3. So to minimize this, so this equation can be further be minimize x star, and this is 4.8 minus x over 0.1, okay, and square no, okay, because this is like covariance can be put into the inside components, and that's why it's 5.3 minus x over 0.3 and square, okay. So this is a one-dimension equations, right? You can solve it directly. So finally, you can get the state x. So x is actually at this, like within the center of the 2 points. May not be the center, maybe like be close to this one, because this you trust more on this measurement, you trust less on this equation. And how much you trust is determined by this variables, okay? By this variables. Okay, how much you trust is by determined by these variables. So this is for the one-dimension cases. Okay. Okay. So any questions for this formulation? If it's no, let's start with the Kalman filtering. Okay, so before we start with the Kalman filtering, okay, so let's define the problem we want to solve first, okay? If the problem is, okay, if this is the 2D coordinate system, okay? So if a robot is moving like this trajectory, so this is a reference trajectory, okay, the ground truth. Okay, like move from this point to this point, okay? So the GPS provides some coordinates. Okay, tells you X, Y, Z. So maybe X, Y, Z is like, because the GPS is not accurate. Okay, so this is quite noisy, right? If you connect those trajectories, it's gonna be like this. Okay, you see it's deviate from the reference trajectories. So this is the GPS. So this it's a reference trajectory, okay? Okay, so the GPS provides a series of measurements. Ci is equivalent to x, xi. Okay, for example, we use the xi, zy, I. Okay, for a two-dimensional case, xy represents x and y, and I represents the timestamps or the index, okay? Okay, so this is a measurement from GPS. Okay, so the second one is the velocity, okay? For example, from via odometers. Okay, so via odometers provides like, if we define the via odometer with ui, so this is the vx I, vy I. So for example, the via odometer tells you, okay, so the velocity of this seconds is 1 meters per second. Okay, so this is the measurement from odometers, like the via odometers. So the two information. So this is the GPS. Okay, this is GPS and odometers tells you velocity. And also velocity measurements from odometer also have some noise. And GPS also have some noise. So let's look into the results first, okay? Okay, later I will let you try the code, okay? So this is the ground truth. Okay, the green dash line, okay, this is ground truth. So red dots here, red star here represents, so this is the position of the GPS provided by GPS, okay? So after you do the fusion, okay, the result is the blue one. It's much close to the green one, right? So the fusion is from the red dots from GPS and some via odometer information, the velocity. So if you integrate two information, you get from red to blue, more close to the green curves. Okay, so let's try a little bit. So in here, there's parameters to tune the noise of the like the GPS. So for example, in here, I assume the noise of the GPS is 0.9 meters. So if I set this noise to about like 0.05, so result is much better, right? You see the blue trajectory is more close. The blue trajectory is more close to the green one. And much better than the purely based on GPS, the red dots, right? Okay, the solution is use the Kalman filtering. So I'm not going to reformulate the Kalman filtering theory. Reformulate means how it comes from. So it's even going to be much 10 times more complicated than this one. So I'm going to directly start with the equations, okay? So of course you can refer to your slide. So, but of course I'm going to introduce the physical meanings of each equations in a Kalman filtering. So generally this problem can be start with a graph problem, okay? So if you look into the state estimation problem, okay? So let's see just state, for example, this x1, x2, x3, xk, okay? Let's see just state. Okay. So let's just say an SK means the latest epochs, right? Timestamp. Epoch means timestamps, okay? So for each of the X, okay, for example, to be consistent, okay? We use, okay, use K, K. Okay, the K to represents the timestamps, okay? For each of the XK, okay? it includes. So the sk, okay, please be noted, xk is a uppercase, it's a vector. It includes the xk, yk, and vxk and vyk. Okay. So this is just days. This is just days. Okay. So for each of the time stems, so the v odometers, for example, velocity provide the constraints between two time stems, right? So velocity is incremental, it's a relative information. So the odometers will constrain to these connections between states, right? Between time stems. So another measurements, for example, okay, if we have one more measurements, this is the GPS. So for example, this is the GPS Z1, Z2, Z3. Okay, the GPS measurement, this is only single connection because the GPS is absolute positioning. It can directly constrain your state at single time stamp. So this is a single connection from GPS. So this is the unitary or the boundary connection between two states. Between two states. You see the differences. Okay, the connection is like this. Okay, so it's like the GPS constrain your states. Okay, it's an absolute constraint. So the continuous is constrained by the odometers, maybe like the V odometers provide the velocity constraints. So the Kalman filtering is to represent this graph. The Kalman filtering is to represent this graph. So for the first one is the Kalman filtering. Okay, so the Kalman filtering is to represent this graph. Okay, so the first one is S. Okay, the star is S. Okay, sorry, in a lecture slide, it's represented with the T to represent the timestamps. So in here, we use the K to represent timestamps. Okay, it's the same. So ST minus is equivalent to F plus. So so the second part is the covariance. Should be F multiply PK minus 1 minus a plus minus FT transpose. So later I will introduce the meanings for this equation, okay? Plus the Q. Q is the noise of the process. So this process is called prediction. Okay, so the first one is represents the, for example, okay, the first one X is the state. For example, okay, X, let's see here. So this is the matrix. So the matrix represents the covariance. It means how the uncertainty of the state. So how much you can trust on the state. So it's represented by the ellipsoid. Okay. For example, this is A, this is B. So for example, if this is a 2 by 2 matrix, right? So the F is going to be a 2 by 2 matrix, 2 square, 3 square. It means the uncertainty in the X direction is 2 meters square. The uncertainty in the Y direction is 3 meters square. So F matrix represents how much you can trust on the states. How much you can trust on the states. So this is the position. So this is your states. So Q is the noise of the prediction, noise of the prediction. So for example, let's start with the equations, okay? Okay, so this is what we have. I mean, this is the measurements. So this is the stage, right? So at the beginning, we can have the equations that Sk should be equals to Sk minus 1 plus Bk minus 1 Vx k minus 1 delta isn't it? This holds, right? So this is the basic motion model. So the yk is equivalent to yk minus 1 plus vyk minus 1 delta, right? Okay, so this can be right into the equations. So the left side is, and also we can have the equations for the velocity. Okay, we assume a constant velocity model. So Vk is equivalent to Vk minus 1. Vk, this is Vxk equivalent to Vxk minus 1. Vyk equivalent to Vyk minus 1. Actually, we assume a constant velocity model. So this is another constraint. So this can be written down into equations. Sk, Yk, Vxk, Vyk. Okay, so this is the corresponding to the left side. Okay, this is Sk minus. This is going to be equivalent to F multiply Sk minus 1 is Sk minus 1, Yk minus 1, Vsk minus 1, and Vyk minus 1. Okay, so this is AK minus 1 plus. So for this one, okay, so this is to directly coming from this motion model. Okay, the motion model, you write down the motion model into a matrix. Okay, so this is going to be 1, 0, delta, and 0, right? If you write down this into this matrix, and this one is 0, 1, and 0, delta. And this one is 0, 0, 1, 0, 0, 0, 0, 1. Is that correct? So this equation directly coming from the 4 equations, okay? You can write these 4 equations into a right size. So this is X, so this is F matrix. Okay, so this is the F matrix. So the physical meaning of the first equation is to propagate your state from the current state to the next timestamps, to propagate your state from current timestamp to the next timestamp. So this is the F matrix. This is so-called the propagation matrix. So this is the state of the previous timestamps, and this is the state of current timestamps. Okay, so in this case, we solve the first equations, okay? We get to the first equation. So for the second equations, okay, so the F is over here. So the Q is a preset covariance matrix. So it's a non-variables. So in the code later you're going to see the Q, okay? So Q is the non-variables. For example, this is experimentally determined, okay? So later in the slide, you can see the results if you set the Q with different parameters. So the PK is the covariance of your state at the previous timestamps. So for example, if you provide the initial guess, so for example, usually we set the P0 to be a big value, 100 square, 100 square. For example, it means at the beginning, we are not trust at your initial guess, but finally it will converge. So in this case, the first and second equation is clear, okay? The F is here, the P is here, and the Q is experimentally determined. So this is for the first part, okay? The physical meaning, okay, so again, let's go back to the problem we just mentioned, okay? Let's go in a straight line. So the physical meaning of this iteration is, at the beginning, you are here, okay? So next timestamp is it will be approaching here based on the real diameters, right? but the ellipsoid is going to be bigger. Okay, because this is the multiplication. It means if you do it directly, okay, the uncertainties of your state will be bigger and bigger. For next time stems, it will be like this. Okay, so if you only do a prediction, if you only use these two equations, it will be bigger and bigger. So good things for the Kalman filtering, okay, we have the second step. It's called measurement update. So update means it's try to decrease the uncertainties. Okay, the next step is the update. It tries to mitigate or reduce the uncertainty of your state estimation. Okay, so the state update, the equations is, okay, so the first equation is, this is so-called the residuals. Sorry, we are going to use the K. Is equivalent to, C is the measurement. Okay, this is a GPS measurement. For example, xk minus. So xk minus is coming from this equation. So let me finish the equation first. AT is equivalent to P. And that's why is, okay, last equation is pk plus is equivalent to I minus k h. Okay, so this is the next step. So this process is called prediction, and this process is called update. Actually, this equation can be simplified into three equations, actually. So for example, if you directly put the SK here, and you can simplify this into four equations. So the physical meaning of the update is, so if you do it directly, okay, based on the, for example, based on the only the via odometers, it will drift over time. I mean, the uncertainty is going to bigger and bigger. So if you have GPS, because this is absolute positioning, so it can mitigate the drift. Okay, so the first equation is calculate the differences between your measurement and your states. So the H is, so H is the Jacobian matrix, for example, for GPS. So H is the linearization matrix. Okay, the linearization matrix. So in this case, in here, okay, the H is the identity matrix. So usually we have equation is Z is equal to HX. So because in this case, the measurement from GPS is in the same domain with your states. For example, the GPS is XY, your state is also XY. So the H here is, this is an identity matrix. The H here is an identity matrix because they are in the same domain. So the second one is SK. So SK plus this one, this K is called Kalman game. This is directly contributed by the covariance. So for example, okay, if you look into this one, this R is the, it's called covariance matrix of the, okay, this represents how much you trust on your measurements. So R means how much you trust on your GPS measurement. So later in the code, you can take choice. For example, if you trust more on your GPS, the result will be more close to the GPS. If you trust more on the via odometers, the result should be like more close to your via odometers. So this is the result. So finally, after you calculate the K, you can update your states and update the covariance. Update your covariance. Okay, so let's take a try on the code. Okay, I will explain the code. So if you have the, so let me show you how to. Okay, so first, okay, found the list repository. Open a laptop, find the list repository. Okay, if you cannot find this repository, you can just search Wison 1 GitHub. Okay, you can find my GitHub page and open this repository. Take your time. Take your time. Okay, you can open this repository and find this. Okay, have you found this repository? Okay, 10 seconds. Okay, find this repository. Okay, if you already find this repository in the issues, okay, in here, okay, there's issues to tell you how to debug your Python code in Chrome. So click this. Okay, there is a link to the Python code. Okay, to this editor. Okay, online editor. So you can copy the codes from this repository in the sample codes. Okay, there's an EKF over here. Okay, there's EKF. There's an EKF. Copy the codes to here. Okay, to run results. Okay, wait a second. Okay, you're going to see the results, right? Okay, try to replicate the results, and later I will introduce the code line by line. Yes. Okay, that's all. Yeah. You find the GitHub. Okay, okay. I'll show you. Okay, let me know if you get the results here. I will explain the details. The results? Yes, okay. Okay, so let's go through the codes line by line. Okay, so as we mentioned, we have two process. Okay, two procedure. Main procedures. The first one is prediction. So the second one is the updates of updates. So okay, so I just assume you already have some background knowledge about Python. Okay, I don't need to explain the grammars of the Python. So the first line we need to look into the first line is. Okay, this one. Okay, this is because this is a function, so we need to look into the first line. So the first line is the dt. So the dt means the time differences. Okay, corresponding to the delta t in here. Okay, so this is the dt. So it's clear on the back. Okay, so the dt is the time differences, the delta t. Okay, so the process covariance is this is q. Because this prediction sometimes is also called the process model or the process procedure or something. So the process covariance, this one is the Q. So of course, okay, later you can tune the values of Q. Okay, so please make notes. Tune the values of Q, you can see the results differences. So the measurement noise is the R matrix. It means R means how much you trust on the GPS. So the Q means how much you trust on the V odometers. So it means you tune the Q and R means you tune the uncertainties of the R and the Q, of the V odometers and the GPS. So this is the step means how much step, okay? So this is purely for simulation. So the true position is, okay, the true position, because this is a straight line, right? So this to simulate the position of the okay, for example here the position is a straight line. Okay, so in here, okay, the measurements is, I mean the measurements is simulated. So the GPS measurement is simulated, okay, based on the ground truth. So ground truth plus a noise. So noise is generated by the random noise or random distribution. So this is just this is covariance R. Okay, so to generate the GPS measurements, so it means you from ground truth plus the noise. Okay, so generate the GPS measurement. Okay, the ground truth plus the noise. So this is the GPS measurement. So the first part is to initialize the common filtering. Okay, let's go back to this one to initialize some parameters. For example, delta, process noise. So, okay, so estimate position. So if you look into this function, so it tries to update your states step by step. So for each common filter, okay, it do the prediction first. Prediction means the two equations. Then it do the updates. So for the prediction function, we can go to, okay, cannot direct. Okay, so this is the function. So the prediction process includes the two equations, right? The first one is this equation. You see, x is equivalent to f multiply f, fx. Okay, dot means multiplications, right? fx is going to be x. Okay. The second one is the calculation of the p. P is equivalent to the fpf. Okay, multiply the q. Q means the process noise, which means how much you trust on the V odometers. So the second one is the updates. So updates is first one is the measurement procedures. Okay, the first one, delta z. Okay, that's delta z. Okay. So the second one is calculator S. Okay, calculator S. So for example, this you can so-call this name as a residual covariance. The next step is common gain. Common gain is P multiplied H. Okay, PHS. Okay, it's exactly the same as the equations, right? It's super clear, right? Cannot be even more clear. So the next one is after you get to the K, okay, you can do the last two equations, X and P. I say you are quite lucky this year because last year we don't have examples. It's quite difficult to understand. But for this one, okay, each equations associated with each line of the Python codes. So lastly, you can calculate the P. Okay, the P is I. I means identity matrix. Okay, I is identity matrix. For example, like I 2 by 2 means this is identity matrix 2 by 2. Okay. So finally, okay, so you can get your states. So please take try. Okay, several things you need to try. So first, please try to tune the process covariance. Tune this process covariance to see the differences. Okay, 10 minutes. So if you didn't take your laptop, so feel free to come here to take try. Okay, Chen Jun, feel free to take try if you didn't take your laptop. So you tune the process knowledge, you're going to see different results. Go ahead, take try. See, our tune the parameter segment to get different results. Basically. this is the perfect case. The measurement noise is 0. A lot of people try to tune the R. R means how much you charge on the GPS or how much you charge absolute measurements. If you tune up, it's going to be different. So if you set measurement values to be 0, it's going to be, the result is going to be exactly the same as the ground truth. 0 is less no noise measurements. So called it's going to be perfect. Also, you set process noise to be 0. If you tune this to be 0, take a look, it's going to be. It's all good. Because it means you have very good real odometers. It means there's no noise on your real odometers. It means you trust you fully trust on the real odometers. Okay, thank you, Chen Jun. And also, I want to emphasize is still you can take this chance to make yourself like GenAI. Okay, so for example, if I feel like this example is not good enough for me, okay, so if you feel like this example is not good enough for you to fully understand the Kalman filtering, so you can search, you can ask ChatGPT. And also, for example, in the final presentation, so for example, if you read some papers, it's related to the Kalman filtering, so you can provide example. For example, you can provide example for a Kalman filtering to fuse the GPS and MU, and you can ask the ChatGPT to provide the example codes. You can change it and provide some results to let us know what you get from the Kalman filtering. So because you can use your smartphone, actually, you can use your smartphone to collect data. So this can also be very interesting. Okay, so you may not be, limited to the topics I provided in the Excel, in the docs. You can choose some topics that you think is very interesting to you and you wish to present. Okay, it's not limited to the topics I provide. This is a very great example for the object tracking. This is still estimation problem. Let's object tracking means the positioning tracking. The position tracking. This is the same. This is the same. So, for example, let's ask the ChatGPT for another example. Okay, so this is an example like, okay, so I just asked a question with ChatGPT to say, so provide a Python example for the velocity estimation only, okay, and plot the results. So it will provide this example. So for example, it's like the state here repeats, the state here includes the x, okay, the position velocity and position velocity in x and y direction. It's kind of similar to our previous example, very similar to our previous example. So I also provide a very detailed, okay, in the issue, okay, I provide a very detailed link here. So this is a very good example. I mean, so because today we only have one lecture, it's just a comment filtering. So in here there are some more examples for the extended comment filtering. For example, if the model is nonlinear, so how to copy the nonlinearity from the model. So this is going to be introduced in the next week. So talking about the extended comment filtering. So before we start the next lecture next week, you can take a look on this. Okay. So for example, we talk about the linearization process. For example, if this is the quadratic function, so this here is nonlinear, right? So it will do the linearization for this point. So after the linearization, this model becomes a linear system. So this you can use the comment filter to solve problems. So through a linearization by doing the calculations of the partial differential. After that, they provide the, okay, for extended comment filtering. Okay, let's finish this tree. So it's quite similar to this one. So the major difference is for H, we need to do the linearization to the partial differential for this one. So the other part is exactly the same, perfectly the same. So later on, they provide examples, for example, the tracking of the airplanes. So for example, if the measurement here is not x, y, z, it's going to be a changing function. So tangent function, of course, it's not a linear case, right? For tangent function, it's not linear case. Another argument here is theta, and for okay, that's good. This is kind of linear. It's quite similar to the GPS. So the model is too small. So for example, for this measure model, this is a nonlinear case. This is a nonlinear case because the first measurement is the tangent function. So we need to do the linearization first. Okay, so that's also be issues in the this week. Also, the F matrix is the same, and okay, so for the H matrix, we need to do the linearizations, right? This is very similar to the GPS part. So we need to do the differential for the H corresponding to the X is the state. Okay, after the linearization, you can get the partial differential H. Also, they provide examples. So you can take a look on this link first before we start the next week. Okay, the link can be found from these issues. Okay, the issues here. Okay, this one. Extended common filter. You can take a look first. Okay, so for this common filtering, so any questions from equations to the examples? Any questions? So after that, you can try examples in your laptop. Okay, so next week, also take your laptop, okay? Next week, we will still provide the examples for extended common filtering. So if you really understand the solutions of common filtering today, you should be able to at least use the measurement from linear models, like X, Y, like velocity. So by next week, if you finish the extended common filtering next week, you should be able to use the measurement from any nonlinear models. Should be good now to use any nonlinear models. Also, for the lecture, for presentations, so if you want to seek my comments, so for example, if you make your presentation at big talk or 30, if you want to see my comments, so you can send your slide to me first. I will provide some comments for your slide if you wish. Okay. And also after your presentation, in the Q&A section, I'm going to provide some suggestions for you if you wish. Okay. So let me take a look if you have selected topics. One, two, three, four. So we still have 4 vacants, still 4 students did not select. Okay, so again, I'm going to finalize the schedule by today. Okay, please select your topics as soon as possible. So I think that's all for today's lecture. I will stay here for additional 5 minutes. So for those questions, if you have questions, feel free to come. Okay. Okay, see you next week.